I'm presently employed as a senior information security analyst for a Fortune 500 company, at least for another week. I actually gave my resignation and I changed jobs in a week.
Quitting unexpectedly.
Yes. So I also do a lot of independent research. The Layered Defense Research Group is kind of like an independent. We don't make any money. We just spend all of our spare time hacking. So the best way to describe me is I'm a threat and vulnerability specialist. I have a passion for security. Love sharing security with others. And I believe the greatest weapons in the hands of a security professional is knowledge. So that's why we're here today. So this presentation, man, this thing's wow. We're going to be discussing the building blocks of format string vulnerabilities. This is a comprehensive understanding of format string vulnerabilities. It's a deep knowledge presentation. We're going to be covering some advanced exploitation concepts. Thank you. At least my ears ain't echoing now. And this is very demonstration intensive. So hopefully we won't have any problems. Of course, the information provided in this presentation is for educational purposes only. So if you go home and crash everything at your present employer's place, and don't blame it on me. So the question here, what is a format string? Well, a format string is a ANSI specifier that is supplied to a function to tell the program what the format of the output should be. It's real simple. You put a specifier into a function. The goal is you want to tell it how to output the data. As an example, you put data, you want to output it to a file, you want to output it to the screen. You have to tell it what format that needs to be in, whether it's in string format, numeric decimal format like hex or decimal or octal. And that's what a format string specifier does. A few of the format string specifiers we have listed up here is %s is for character string output, %x is for hexadecimal, %u is decimal, %n is a special format string specifier. It actually keeps a running count of all the output from the function. That uses the format string specifiers. So that'll come in real handy later, and you'll see. And this is not all the format string specifiers. This is just a small sample of them. And the main ones we're going to use in this presentation are %s, %x, and %n. So here's a list of a few functions. This is not all of them, just a few that utilize format string specifiers. So understanding the vulnerability. Where does vulnerability come from? Well, the vulnerability was first discovered and made public in September 1999. The first exploit code was released in 2000, and it was for WFTP 2.6. Since then, a few hundred, maybe, I don't know, 300 or 400 format strings have actually been made public. The vulnerability has been made public. So they're fairly, I don't want to say scarce, but they're a lot more rare than buffer overflows and those type of attacks. Most of the format string vulnerabilities that have been disclosed so far are within the Unix environment. A lot less of them within the Wintel environment. Our presentation today, we're going to focus on the Wintel, because there's been a lot of focus on the Unix environment. So there's a lot less format string vulnerabilities have been reported in Wintel. So what is a format string vulnerability? Well, we know what a format string is. So where's the vulnerability come into play here? Well, a format string vulnerability is caused when a programmer does not supply that format string specifier in the argument of the function. The reason for that, a programmer may be taking shortcuts, he's being lazy, or just pure lack of experience. Now, before we go forward, I want everyone to understand I am not a programmer. I was talking to my friends today, and I said, I need to take a couple more programming classes so I could actually get my skill level in C++ up. This sucks. Okay. So I'm not a programmer, so I approached this whole thing with very little programming background. So I've tried to make this whole presentation take it away from the C programming and carrying out an exploit. I've been too many presentations where you see exploits carried out, and you're sitting there going, well, I'm not a programmer, and I just seen like 14 pages of code. What the hell does that mean? We're not going to do that. We're actually going to carry out some attacks and exploits and vulnerabilities using raw format strings and pure ASCII input. So that'll make this a little more funner and definitely a little more for the broader audience to understand some of these things. So we're going to start at the bottom and we're going to build up. And then at the end, we're going to demonstrate a couple exploits in real applications. So let's start out, let's look at some code snippets, because you got to have a little bit of understanding of code to understand where the format string specifiers and where the format vulnerability comes from. So here's a code snippet, and we're utilizing printf function. Now if you take this code snippet and compile it, it'll run, and we're actually going to do that, have a compiled copy of this we're going to use in a minute. This is the actual correct use of a format string specifier for the function printf. As you can see right here, %s, we've told this to take this argument, printf's, output it using the string format specifier, output it as standard text. Pretty straightforward. The incorrect use of this is this one right here. The only difference is, as you can see, the printf function, the format string specifier is missing. This will compile and it will run and it will appear to run normal. So let's go ahead and start off with some short demonstrations so that we can have an understanding of that. Let's go ahead and change this prompt. Okay, so let's look at correct. Let's go ahead and pass the infamous hello world. And it outputs hello world, quite normal. If we pass numeric data to it, the correct program outputs numeric data. If we pass format string specifiers into the argument, it outputs those as standard text data, nothing special. So let's go ahead and look at incorrect. We pass hello world to the incorrectly built program, it works fine. We pass numeric data to the incorrect program and outputs it as numeric data. So where we see this whole thing break down is when we pass format string specifiers to it. Instead of enumerating this and output it as standard text, it'll actually read the process's stack. And at this point, it will output data from the process stack. So that's what a format string vulnerability does. Gives you the ability to look behind the scenes and do some nasty things. Okay, let's move on to the next level. Exploiting this vulnerability. So what can an attacker do from here? As you saw in the examples, it's real easy how the specifier is left out of the program becomes vulnerable. And you saw that an attacker using %x can pop data or read data off the process stack. Well, you notice those numbers that came back. If we would use a %s instead, it will take those numbers and evaluate those as pointers to memory. And it will go to that location in memory, and it will start reading at that point and read the memory until it hits a null byte or zeros. So with %s, we can read memory. %n is even funner. %n keeps a numeric count of all the outputs from that function during that execution. If you use %n, it'll also enumerate that value off the stack as a pointer in memory. But instead of reading it, it'll actually write that pointer, that counter number out to that memory location. So using these three things, we can read data from the stack, read data from the stack, read data from memory, and write in memory. So we're going to use these three in this presentation as we proceed forward through systematic stepping through this to carry out these attacks. So let's go ahead, and we've got some more demos. We've got a simple program we put together, a GUI program that is vulnerable. It's a bad piece of code. And this program right here is vulnerable. So if we put format string specifiers in it, we go print, it'll actually read from the stack. And if you notice, it read 2, and then a 0, then a 0, then a 0, then a whole string of data. If we actually run this again, or a couple times, you can see it actually changed. Now it's reading from the same memory location, so take note of that. We're reading from the process stack. The process stack is a very dynamic part of memory. Okay, so it can change, and our program here shows that real strong, that it can alter and can change. So we'll have to take that into consideration as we move through carrying out exploits. So I'm going to stay sitting for right now. And the next goal is, as we read from the stack, we had to read the memory locations that were given to us on the stack. So the attacker's goal is, can we put our own data on the stack? And it's quite common. A lot of times when you input data, that data is stored on the stack. So if that particular function that you're inputting data into stores data on the stack and it's still vulnerable, can we put data on the stack, read down until we find that data, and then enumerate that as a memory location? Basically giving us the ability to write arbitrary memory. We can control those pointers that we can read or write. And our vulnerable program obviously has that problem. As an example, we're going to put A's right here. We're going to put 4 A's onto the stack, and when we go print, it'll read those off in hex. 41414141. So now if we would put data in the place of those 4 A's that was equivalent to a memory address, we could potentially read or write that memory address. And that's where we get to the next point, reading memory. So what we want to do is actually, I don't need that, shut that one down. We have a couple of cheat sheets to speed us through this thing, reading demo. So this right here, this ASCII string right here, is actually equivalent to this memory address, 77E47670. So if we replace this with an address that truly does exist in memory, verify it's the right address, 77E47670, and we change this to an S and go print, instantly we've read that memory location. Where it starts reading at that memory location, we'll continue reading until it hits a null byte. Okay, so there we go. We were able to read arbitrary memory, control the memory address that we could read. So you say, well, what value this has? Well, I got a great story and a good demo. You'll love this one. Let's get out there. Having fun with Novell. How many people have experienced working with Novell? All right. You'll like this one. There's only a small group of people who have actually seen this exploit. So, and it was patched about 8-9 months ago. Here, let me bring this up. Remote desktop. Before we get started here, I forgot to hook up my network cable, so we may have a little problem connecting. I apologize, getting in a hurry here. Okay, let's let that think about it a second. Let's explain this story. The first format string vulnerability I found was in Novell. Was in Novell's logon prompt. So it was real simple. The only thing I could do was read off the stack. I could write data to the stack, but it was so far from the starting point when I started with the %X's, I could not read far enough down to get to that. So the only thing I could do was read from the stack. I couldn't read from arbitrary memory, and I couldn't write to memory. So it was purely reading from the stack. So I called Novell and said, look, you have a format string bug. You can't do much with it, but you need to patch it. So I contact Novell, and hopefully it connects up. I contacted Novell and told them about it. I think about 5 or 6 months went by, And Novell released Service Pack 2 security patch, I think it was C is what they called it. Just to show you how this works. Sure this works okay. So when we sequence en masse, come on, it would actually come up. And as you can see we read from the stack right there. So the only thing we could do with the original vulnerability was read from the stack. They released the patch. I downloaded the patch and installed it on my system. And instead of fixing it, they actually made it worse. So now I can read arbitrary memory. So I contacted Novell and said, look guys, you made the problem worse. And they said, okay Daryl, we'll go ahead and we'll fix this and we'll let you know. 4 months go by.
And they sent you a cease and desist letter?
I would have been happy with that. That would have meant they took it serious. So 4 months go by, and they released Service Pack 3. I said, finally, they fixed it. Novell's real bad at not telling anyone when they fix things. They just fix it. That's just the way they are. So I went ahead and downloaded, installed it. At least this time they didn't make the problem worse, but they didn't fix it. So I'm pretty much pissed at this point. We're looking at almost a year. So I sent them another email. So look, guys, you obviously don't care. Since you don't care, I'm going to go ahead and release the advisory. So I thought they'd come back and say, oh, sorry, or something. They come back and go, no, they go, Daryl, you're right. Go ahead and release your advisory. We ran this through our development team, and they do not think this is serious, and they don't plan on patching it anytime soon. So I went ahead and released an advisory on a Friday, and I sat down on Saturday, and you know, I'm sitting there going, how can I make their life hell? So the advisory is out there, so let's see if I can get this right without screwing it up, because this is all live. So I sat down and started digging through memory. There has to be something they don't want me to see, especially remotely. This is a remote desktop. Let me go ahead and get my number lock key on. So I found something real interesting in memory. You'll like this. If you didn't know you can type those characters in, you can if you hold down the Alt key and put in decimal. So this memory location here, and let's look at the memory location. It comes up, it's 52E1F221. So I packed this up and sent it to them. I know everyone's on the edge of their seat. You want to see what that is? I had to patch in 3 days. Wow. It's actually 3 business days because I shot him the email on Sunday and said, gentlemen, this is why I think this is important. Please enter this in at the login prompt and click sequence. The email I did get was from one of the head managers there, and he literally said, Daryl, shit has hit the fan.
Got a question.
How did you find that? Fuzzy searches?
What's that now?
How did you find that fuzzy?
No, I don't run any fuzzers. I usually do most of the looking for this stuff in manual testing. And we'll talk about that at the end if we get there. Okay, so let's see if we can go forward here. Writing to memory. Now we talked about reading from memory. Let's go ahead and do some simple test writing to memory, just so you can see how that functions. Okay, we're going to go ahead and use this program here, but don't do that. Come back here. We're also going to bring up Ollie debug. And we're going to open an Ollie because I want you to see it actually in the program as we're altering the memory, just so you can see how this function takes place and what happens. Let's go ahead and attach it. Get it running. Come over here to memory. So let's go ahead and look at this. We go print. Come back here. Probably need to shut some of these down. I mean, so many windows open, the box is going to dog out on me. So just be patient with me so I shut some of this crap down. Okay, so what we want to do is we want to go to that memory location. 77E4. So we come over here, 77E4 7670. Right there is the beginning of that memory location. And as I mentioned, remember, it starts reading, and it'll read from there until it hits the null byte, which would be right here. That's the null byte. And that's how the program reads. You start reading from memory, it'll read all the way until it hits a null byte. So let's go ahead and do some writing in memory, okay? As I mentioned, the output of the function, the character's output will increment the %n counter up, and that's what you end up writing in memory. So if we look at this and we count this, you can see over to this point right here is 8 characters. Ignore the end address because we're going to change that over. So if we go %n, go print, if you come over here, you can see we overwrote that memory address with 08. Also take note that the last preceding 3 bytes are overwritten. You can only write 4 bytes this way. So you're always, if you only write 1 byte, you're always going to overwrite the preceding 3 bytes. Also, notice that these characters right here is just 8. Remember, it's 1 character output. If we do it again, now that the stack's changed, this number is going to change also. And you see it's actually changed to 20, which is a decimal 32. So that means there's 32 characters were output by that. So the goal to stabilize, one of the techniques for stabilizing that output so it isn't changing on you, is to pad all of the output. So this will set it at 8 characters. Anything that doesn't have a real character in it, it'll pad it with a 0 and output it. So at this point, this will set this, and the output will be fixed at, in this case here, should be, I believe, 24, which should be 36. There, 24 and 36. So that's the most simple approach to this. Okay. One other thing we want to cover is, at a minimum, format string vulnerabilities can be used to at least cause denial of service conditions. Anytime you try to read or write a memory location that is not legal, you either can't write to it because it's a read-only location or it doesn't exist in memory, the program is going to crash. And in this example here, if you notice, we have an access violation writing to dead beef. So the program will crash that way. Okay, let's see if we can proceed on. Some of the limitations an attacker will face, at least from my perspective. In the Windows environment, base addresses change. So if you shut a program down and restart it, the base address of the stack is typically going to change. So if you need to be writing addresses to the stack, that becomes an inherent problem. The one good thing, even though that stack may change, the key thing with format string vulnerabilities is it's usually some kind of write function, an output function. And a lot of times you can get that output function back to you as an attacker. So if you can get that output back to you, you can figure out what that base address is prior to carrying out the attack. Also, anything with null bytes in it becomes an inherent problem. Stacks that are low in memory starting with 0, 0, carrying out attacks this way using just format strings and ASCII input to carry out the attacks. It's kind of hard to put a null byte into a standard string. Now you can do this in a lot of cases programmatically and may be able to get around some of these problems, but it adds a complexity to the situation. Limited write counts. And what I mean there is it's dealing with buffer sizes. That %n is a buffer. It counts up. So within the program, it may be limited on how high that can go. Or it may be limited on how high it can go. Also, as an example, you notice we put that .8 in there to pad that up. You can make that number a lot bigger and write a bigger number. I've run into situations where the buffer would only allow that to go up to, let's say, 512 or 256. So if you're wanting to write a 4-byte address and you get up into the address range starting with 77 and eat up all 4 bytes, that's actually upwards over 2 billion. So to pass 2 billion characters into some buffer is reasonably impossible. It's doable. I've done it. One of the exploits we had done, I was able to write the entire 4-byte address in a single %n write. The problem is when I kicked it off, the machine 100% CPU for 7 minutes trying to generate over 2 billion characters output to a pop-up window. It worked. I got code execution, but you know, if you're really trying to develop a real attack, expecting somebody to wait 7 minutes might be a little ridiculous, but it may be possible. Also, as I showed, you can only write 4 bytes with this. If you write a single byte, the preceding 3 bytes will be overwritten or damaged. So what technique do we use to get around the fact that we cannot write 4 bytes at one time? Well, we do it in 4 separate stages. We write each byte separately, incrementing %n up between each one of the writes until we overwrite our 4 bytes and get our address. So in this example here, we show this. We do the first write to this address here. We increment %n up with the dot numeric value that we showed before the X, and then we write it out. And then we increment it up in between the 2 writes, and we write it again. But FD is lower than FF, %n cannot be decremented, can only be incremented. So at that point, we got to increment it up past FF, so we end up writing 1 FD. Windows is a little Indian, so it's kind of reverse byte order. That's why you're saying, well, why are you reading it backwards? Well, it's the way it is. So FD, if we want to go to 7F, which is lower than FD, we have to write up over to 7F. And by following this technique, we can actually write 4 full bytes in an address. An example would be overwriting a return address on the stack. And we can do this in 4 stage steps. We're actually going to go through this process right here so you understand it. We're actually going to demo it. And then we're going to take everything we've talked about so far and we're going to apply it into a proof of concept attack against semantic antivirus. So this here will take a few minutes to get everything up, but
Sorry, guys.
we're going to bring Ollie Debug up. We're going to go ahead and use our demo program. And then we also going to bring up a cheat sheet. In the cheat sheet, we're going to go ahead and write 7F, FD, FF, FC to a memory location. Ignore the cheat line right below that. And then we have I've already converted everything in a certain memory block area so that we can actually do this. We go all the way down. We need to find a section of memory where we won't crash our program because we overwrote something. This is a live running program. So we're going to come all the way down to this end, and we have 7F FD, FF, F0, FF, F0. So here's the memory area that we're going to end up writing. So the first thing we want to do is get all of our individual addresses. This is the first address. We put the A's in between so we have the ability to increment %n up and have control over that. If we tag all the addresses right against each other, then whatever we put in %n will be the same across all address spaces. You ask why we use A's? That's because we're not using B's. Doesn't really matter, whatever choice you want to use. Okay. Put a few spaces in there so we can initially test this. And you can see there's our first address, our second address, third address, and fourth address. So everything's looking good here. So the first thing we want to do is we're going to pad up these addresses here, because remember they're constantly changing on us. We want to make sure they're fixed in at 8 to start with. And then we're going to go ahead and change our %x's over to n's. And hopefully we have them all in the right place and I didn't miss nothing because it will crash. Okay. First address, second address, third address, fourth address. We go print and we come up to the memory location, and there we wrote the 4 addresses. Now we're writing correctly the 4 addresses. If you notice, every one of them incremented up by 8. There's 8 bytes between each one of them numerically. So the next step is we need to write our address. And it's purely a math game. It's not rocket science, but once you initially get your program writing correctly, the next step is bring open a calculator. And of course, turn off your num-lock keys so you can actually type something in. You know, I practiced this demo like 40 times, and every time I did that, you think I'd learn after like the 39th time.
Unless you really know all the alt sequences for all the characters you want to type. Then you're a geek.
Okay, so we bring up a calculator. And it's real simple. First character we want to write is 7F. So the best way to do that is 7F. We have the 3C, so we subtract 3C from it. And then we want to go ahead and add 8. The reason why we add 8 is because remember we had padded those bytes with 8. So we need to, since we're taking that out, we need to re-add it. And convert that to decimal, which is 75. So then we bring up our code here, and we go to the last padded 8, padded X. We change that to 75, and we go print. We come up here, it should say 7F. And we follow that sequence. The next one we want to write to, is FD. We follow that same thing. We're going to do a couple of these and then we'll just fill it on out. FD, and the number is 87, so we want to subtract 87 from there. And then we want to add 8 back in. And then we change this to decimal, and it should be 126. So we go to the next write, which is this one right here, for writing our next address, and we go dot 126. We go print, come up here, and it didn't work. Okay, that's why. I'm surprised that didn't crash. Thank you. Okay, FD. So there we go, and then we can finish it on out. I think the next one is 258. Let's double check. I think I know this by now. 258 and 253. Yeah, 258, 253. At that point, we've written all of our addresses as we expected. And that's the four-stage write method. And it's this format string vulnerabilities is a big numbers game, as you can see. Just a matter of figuring out what you want to do, calculating out the reaction you expect to happen, and carry it out. Now the exploit we're going to get into here in a few minutes. Is there any questions? Silence. Okay. Now what we're going to do is we're going to switch over here and see if we can do this live demo without screwing things up. Should have come up in a minute. There we go. Since we're making some good time, I can be patient and hopefully not screw this thing up. In this demonstration, one of the things you run into, and I actually ran into it last night when you're carrying out these type attacks, where you're inputting the raw ASCII data attack, there's certain characters you can't use. I mentioned that 00 or a null byte can't be passed that way. Also, 0A cannot, and neither can 0D. Those are carriage returns and line feeds. And if you try to put those in a window, it will carriage return and line feed on you. And then if you pass it through, the system will process it as space. So it inherently doesn't work. So the base address on this program is always changing. Last night, when I was going through the demo, it came up as a base address of 050A. Instantly, the exploit wouldn't work, so I had to reboot. So we have time. If something weird like that happens, it still gives us enough time we can reboot. So did everyone get my password there? How many people here use Enterprise Norton Semantic Antivirus Enterprise version corporate at your business? Okay. This was the second format string vulnerability I found. Sitting there playing one day, and I got a virus on the machine, and all at once this pop-up window came up and said, "You got a virus." And instantly my brain goes, "Huh, I wonder if I could alter what's in that box. Could I carry out an exploit?" And the answer was yes. In version 8, version 9, version 10, and the personal security, everything that Novell put out that had a pop-up box was vulnerable. In this demonstration here, for simplicity, I'm going to use, and this is purely for simplicity, the tamper protection pop-up. It's easy for me to trigger. It's only a proof of concept. You would typically have to have elevated rights to alter what's in this box. But an attacker can use or define his own scans and control the pop-up box himself in every implementation. They patched this about a year ago, and about the time they released 10.1 is when they patched it. Because I gave them the information prior to 10.1 going live, and they fixed it before they took it live. And they went back and then repatched 10.9, and 8 was never patched. So if you're still running on 8, you're screwed. So if we look in this message box, we see these X's. I don't know if anyone's ever messed with Semantic, but you have all these pop-up boxes that tell you what's going on. So in tamper protection, the routine is if an attacker tries to shut it down, it'll prevent it and throw up a box. And if you notice, we didn't get the %X's. We actually got format or data off the stack. So instantly we're vulnerable. This vulnerability is fairly complex, and it become a real numbers game because we had to, I can't remember, we had to pop, gosh, how many was it? I don't know, it was like 2,000 or 3,000 bytes off the stack to get to our code. but our output couldn't go higher than 1023 or truncated the entire tag. So we actually came up with some new techniques for reading data off in the Windows environment and format strings. At least I think they're new. I never saw them referenced anywhere else. And we're going to have that at the end so you can see that and talk about that a little bit. So the first thing we wanted to do in this attack is, let's bring up, oh gosh, where's my code? First thing we want to do is, when I start this thing and get all this weird data in here, we need to make sure we execute it because sometimes it'll crap out with that stuff sitting in there. For some reason it checks it and goes, oh my gosh, what did I do? Pukes on itself. So the first thing we want to do is get the base address of the stack. And hopefully it doesn't have a 0A in it. The question is, do you guys feel lucky? We got time though, we can recover from it. Could be one of those days where it won't do anything but 0A. So we go ahead and in process. And we end up with 04FB, so we're good. So this is the base address, 04FB. Like to run WordPad, we're going to go ahead and put 04FB in there. Little endian, remember that. And then what we do is we use Alt-X and convert it over to some form of ASCII. What we're going to do is we're going to go ahead and run through the exploit, and then we're going to come back and look at the code so you can see what we discussed, all the stuff I showed you, being implemented in a real piece of exploit code. Now, before we save this thing out, we have to come back here. 04FB. If I got that right. Copy that out, and now we need to set the base address of our addresses. This is the first address. The second address. The third address. The fourth address. Looks like it's all there. What we should do is, if this all works, is we throw a command prompt at system level. So if we come over here and we look at this, we are running at system level. So any of the pop-up boxes within the product, you can get code execution at system level. What was interesting is a presentation I put together last year for, and then it crashes. I was working on a presentation last year where we took this, and it never got used, the presentation didn't get used. I spent some serious hour on it. It was kind of cool because the one thing about semantic antivirus, you can also have all these pop-up information sent out in emails. The system will let you do that. So we built this attack where we could actually go onto a semantic system console, and there's various ways to break into those. Pick a target anywhere in a corporation, go to that target, make a quick configuration change to send everything to us in an email and not alert the user, and then we send him a virus in an email. It'll never open it, but as soon as it shows up on the box, Semantic would look at it, not even tell the user, would trigger the code, send us back the base address. Then we turn around and send him, plant the code out there, send him another email, and then get full code execution on the remote machine just using the semantic system console and passing code back and forth that way. So it was a cool exploit. Really complex because we found out that our window, our process thread wasn't one thread, there's 3 threads, and they rotated. So you had to calculate the base addresses of the rotation to pull it off. And it was very doable, but somewhat complex. So let's go ahead and look at this code real quick, if everyone can see that. So here's the piece of code that we use. If we come out here to this point right here, Can everyone see that okay? This here is a simple piece of assembly code that was actually just converted to ASCII. And all it does is a create process. Standard create process command.exe. Nothing really complex about it. And then we have our 4 addresses. This was the first address, the second address, the third address, and the fourth address. And what we were actually overwriting with these 4 addresses was actually the return address on the stack, one of the return addresses. Now our code was actually, the code up here was actually sitting on the stack also. And that becomes very complex because remember the stack base address changes. So we can go into the code and change the base address. But if the code we're jumping to is on the stack and the base changes, instantly our numeric calculations for %n would always change. Oh man, it's just pure nightmare trying to carry out the exploit. So what you do is, what we did here is we used a trampoline off another memory location. So in this case here, we trampolined off msvcp71.dll. And what we did was we found the location it did what's known as a pop-pop return. So what it would do is it would jump the execution off to this location and it would read the stack. It would pop the first address off the top of the stack, the second address off the top of the stack, and the third address it would say, use that as a return address, go to that location. Well, that third address down happened to point to our code on the stack. So instantly we use that pop-pop return by bouncing on trampoline off an MSVCRT71 and jump straight back into the program, or back into the stack, executing our code. I know it may sound somewhat complex to everyone, but it's really not that complex. If you get a chance to dig into that a little bit, if I can figure this thing out, anybody can figure this out. It's a lot of fun. There's a lot of good white papers out there on this subject too. And I spent a lot of time reading those white papers when I first started doing research into format string vulnerabilities. So what am I trying to install here? This is my work computer. Techniques for discovering format string vulnerabilities. Fuzzing. Fuzzing seems to be a big technique lately. You hear everyone talking about it. I don't normally use fuzzers. The thing I found out, and it was real adamant, I had Carnegie Mellon Research that does the search stuff contact me on one of the vulnerabilities because they tried to recreate it with a fuzzer. And this guy, I don't know how many days he spent fuzzing this application in the area where I had this vulnerability, and he couldn't discover it. The reason why he couldn't discover it is the typical fuzzers carry out a single operation. They input data, expecting the program to take the next action. Input data, program take the next action. And it's real common to find format string vulnerabilities where you input data, go to another location to trigger something, which causes that to read that data, or you trigger an edit mode. So it's a multi-step function. And a lot of fuzzers are, maybe some of the ones they have now are getting better at that, but complex actions within a fuzzer, you don't see that very often, so it's more difficult to find that. So in my opinion, there's probably a lot of format string vulnerabilities being passed over by using fuzzers. So I do manual testing. I sit down at work and I do my job. And every time I see input echoed back to me, I assume there's a format string vulnerability there, and I test for it. Error messages contain my input. I love error messages. You can screw things up really bad. User can process a job or name the job that's processed or executed. How many things you do at work in a system that may run at system level on a server where you as the user can tell that program where to get a file at to process it, or do this or do that. You can use format strings in the names of files. You can use format string specifiers in path statements. So you can actually change the file name or path name for something and carry out a format string vulnerability. And always the ultimate thing is just type in %s and everything and wait for it to crash. That works really good. It can be fun. I recommended somebody, maybe I ought to get my name changed to %s. Bring down all the government computers. So these techniques here, when I started doing this research project, my goal was to learn format string vulnerabilities. The first one I discovered was the Novell one. The second one was this semantic antivirus. That one got my attention. I said, oh, geez, what about all the other enterprise antivirus programs out there? So I went out to the top 10 list, and I grabbed the next one in line. I discovered a format string vulnerability that was in CA's product. So I went to the next one, Trend Micro. Hey, I found a format string vulnerability in Trend Micro. And went to the next one, Bitdefender, format string vulnerability. F-Secure, format string vulnerability. I think the only, and I kind of got bored at that time. It's like, all freaking messed up. So I went to the funny one. I went to, I got this here. I looked at McAfee. I couldn't find a format string vulnerability in it, but I did find a buffer overflow. By accident.
Even better.
I didn't really do nothing with it because, like, hey guys, I'm like working on format string vulnerabilities. Don't be giving me buffer overflows. The CA product was their big enterprise product. I think I found like 4 buffer overflows by accident. It was like, oh, this is a piece of crap.
Keeping you safe, right?
What was interesting with the McAfee, if you have enterprise version 8.0i and you go to the window and it says the buffer overflow protection thing, you know, they have that buffer. There's a thing called buffer overflow, so you can put exceptions in so programs aren't processed for buffer overflows.
Right.
It was in there. So back to the techniques I was talking about. If you've seen the code over here, you notice there was a lot of %, commas. And what that actually does is like I mentioned on this attack, we had very limited output space. That means we had to write 4 addresses, 4 individual addresses using %n by incrementing them up. And the biggest number we could write hex was 3FF. Biggest number. Now we got to write 4 addresses of that and read like 3,000 bytes off the stack. So how do we do that? Well, I found out if we use a %* and put some character after that, I happen to use a comma, what it'll do is it'll read 4 bytes off the stack, but it'll only output 1 character. So if you had, let's say you read AAAA off the stack, the output would be 8. It would be 4141414141 and adds up to 8. That means %n would increment up by 8 characters, or the number 8. By using this technique, we can get the same amount of data off the stack, but only increment up 1. So instantly now I can read a whole lot of crap off the stack without ever incrementing %n beyond the ability to carry out the exploit. And that's great for if you have limited output space in the buffer. For limited input space in the buffer, you know, we put in a %x, we read off the data. If there are only 0 sitting in that buffer, we still end up having to put in 2 bytes, the %x. So if you're limited in what you can input, this comes in handy if you only need to read zeros off the stack. There's a %f or a %g will actually read 8 bytes instead of 4 bytes off the stack. So if you're only looking at zeros, this one happens to be floating point, and this one, I believe, scientific notation. So it has to be zeros in there, because if not, you're going to get like really big numbers off there. So this gives you the ability to read data off the stack with more limited input. So I can get twice as much off the stack, or read twice as much down to the stack as I would with %x. And you'll find out in some of these attacks, you'll find large sections in the stack that may be all zeros. You take advantage of that by using %g, and I can use half as many characters to get that data off the stack to get to my input data. And like I mentioned, buffer overflows are common within format string vulnerabilities. So you can actually carry out a buffer overflow using format strings. So let's say you can't get the format string to work, to execute, but there's a buffer overflow. You may be able to trigger that buffer overflow or leverage that buffer overflow by inputting format strings. An interesting anomaly that I discovered, and I'm not quite sure why it does this, but on this right here, if we don't use a comma, but we use some character that happens to be a format string specifier, as an example, if you use %x, and let's say you read the number 10,000 off the stack, if I would put in there %*x, it will actually process that 10,000 times and will write into a buffer spaces, hex 20, 10,000 times. Obviously, in a lot of cases, that's going to cause a buffer overflow. I haven't found a way to leverage that yet. But I also found out if you don't use the format string specifiers, you can use this method right here to actually embed. Remember, we're using ASCII characters. You can put any ASCII character there in place of that comma. So you could actually embed your actually shell code into the format string execution itself. I've tested that on a small scale to see if it would work, but you got to remember any format string specifiers can't be used. So it's somewhat complex there. I think that's pretty much it. I hope everyone enjoyed that.
No questions?
Now, if you're going to ask me some advanced programming question, I told you I'm actually a little bit below sucks.
I think I'm even below that. I guess I'm wondering about, where have you looked at, say, Windows operating system, Microsoft Office, that sort of thing? I would guess that's been.
I have not looked at some of the Microsoft products. I've looked mainly, I'm more interested in some of the corporate products you see used. I work for a Fortune 500, or did. And so a lot of the programs I look for are things that live in corporate America, in enterprise-wide type applications, antivirus programs. I've discovered 7 format string vulnerabilities that I've actually reported. Kind of got tired of reporting them, so it's like, oh, format string vulnerability, and throw it in the trash. They're a lot more common than what most people would think.
So here's my question. Does this apply at all to hardware device drivers?
Hardware device drivers.
The answer is yes.
Yeah, if you're a programmer, I would say yeah. I guess so. I haven't seen it in a hardware address driver. But as I mentioned earlier, I had this list of format string functions that utilize format strings, and that is just scratching the surface. There's a lot more of those.
The thing I think you could get away with doing, and I'm no expert at this by any means, but if you have a device that actually has higher...
Nick, thermos.
Get over here then, you're running away on me.
Sorry.
So if you actually have a device that has higher access to memory, like OS contents, you might be able to get away with actually pulling passwords from the operating system.
A lot of the big techniques, and I've talked with other people about it, is remember, if you can execute basically any kind of read or write operation in memory, even if you don't get code execution, you could actually overwrite passwords in memory with nothing. So instantly the password's gone and you're in.
I love Linux because you get to run a lot in kernel space. It's like, oh, just compile it into the kernel. All right. No problem, because that's safe.
Now, out of curiosity, I did actually find a format string vulnerability in embedded hardware on a firewall.
Oh! Was it
a checkpoint device?
No. It was, you couldn't get access without being on the console of the box. But the whole idea that it actually existed there opened up a whole realm of potential exploitation within embedded systems.
Anybody? Anybody?
No questions?
All right.
Well, if you come up with any questions, I'll be here the rest of the weekend. So.
Woo!